Complex zeros. When finding the zeros of polynomials, at some point you're faced with the problem x squared equals -1. While there are clearly no real numbers that are solutions to this equation, leaving things there has a certain feel of incompleteness. To address that, we will need to utilize the imaginary unit I. Imaginary number I. The most basic complex number is I, defined to be I equals square root of -1, commonly called an imaginary number. Any real multiple of I is also an imaginary number. Example 1. Simplify square root of -9. We can separate the square root of -9 as square root of 9 multiplied by the square root of -1. So we can take the square root of 9 and write the square root of -1 as I. Square root of -9 equals square root of 9 multiplied by square root of -1 equals 3I. A complex number is the sum of a real number and an imaginary number. Complex number. A complex number is a number z equals a plus bi, where a and b are real numbers. A is the real part of the complex number. B is the imaginary part of the complex number. I equals the square root of -1. Arithmetic on complex numbers. Before we dive into the more complicated uses of complex numbers, let's make sure we remember the basic arithmetic involved. To add or subtract complex numbers, we simply add the like terms, combining the real parts and combining the imaginary parts. Example 3. Add 3 minus 4i and 2 plus 5i. Adding 3 minus 4i plus 2 plus 5i, we add the real parts and the imaginary parts. 3 plus 2 minus 4i plus 5i. 5 plus I. Try it now. Subtract 2 plus 5i from 3 minus 4i. We can also multiply and divide complex numbers. Example 4. Multiply 4 multiplied by 2 plus 5i. To multiply the complex number by a real number, we simply distribute as we would when multiplying polynomials. 4 multiplied by 2 plus 5i equals 4 multiplied by 2 plus 4 multiplied by 5i equals 8 plus 20i. Example 5. Divide 2 plus 5i divided by 4 minus I. To divide two complex numbers, we have to devise a way to write this as a complex number with a real part and an imaginary part. We start this process by eliminating the complex number in the denominator. We multiply the numerator and denominator by a special complex number so that the result in the denominator is a real number. The number we need to multiply by is called the complex conjugate, in which the sign of the imaginary part is changed. Here, 4 plus I is the complex conjugate of 4 minus I. Of course, obeying our algebraic rules, we must multiply by 4 plus I on both the top and bottom. 2 plus 5i divided by 4 minus I multiplied by 4 plus I divided by 4 plus I. To multiply two complex numbers, we expand the product as we would with polynomials. The process commonly called FOIL, first, outer, inner, last. In the numerator, 2 plus 5i multiplied by 4 plus I, expand equals a plus 20i plus 2i plus 5i squared, since I equals the square root of -1, I squared equals -1 equals 8 plus 20i plus 2i plus 5 multiplied by -1, simplify, equals 3 plus 22i. Following the same process to multiply the denominator, 4 minus I multiplied by 4 plus I, expand, equals 16 minus 4I plus 4I minus I squared. Since I equals square root of negative 1, I squared equals negative 1, equals 16 minus negative 1 equals 17. Combining this, we get 3 plus 22I divided by 17 equals 3/17 plus 22I divided by 17. Try it now. Multiply 3 minus 4I and 2 plus 3I. In the last example, we used the conjugate of a complex number. Complex conjugate. The conjugate of a complex number, a plus bi, is the number a minus bi. The notation commonly used for conjugation is a bar. Conjugation a plus bi equals a minus bi. Complex zeros of polynomials. Complex numbers allow us to write solutions to quadratic equations that do not have real zeros. Example 6. Find the zeros of f of x equals x squared minus 2x plus 5. Use the quadratic formula. X equals 2 plus or minus square root of negative 2 squared minus 4 multiplied by 1 multiplied by 5 divided by 2 multiplied by 1. Equals 2 plus or minus the square root of negative 16 divided by 2 equals 2 plus or minus 4i divided by 2 equals 1 plus or minus 2i. Two things are important to note. First, the zeros 1 plus 2i and 1 minus 2i are complex conjugates. This will always be the case when we find non-real zeros to a quadratic function with real coefficients. Second, we could write f of x equals x squared minus 2x plus 5 equals x minus 1 plus 2i multiplied by x minus 1 minus 2i if we really wanted to, so the factor and remainder theorem holds. How do we know if a general polynomial has any complex zeros? We have seen examples of polynomials with no real zeros. Can there be polynomials with no zeros at all? The answer to that last question, which comes from the fundamental theorem of algebra, is no. Fundamental theorem of algebra. A non-constant polynomial f with real or complex coefficients will have at least one real or complex zero. This theorem is an example of an existence theorem in mathematics. It guarantees the existence of at least one zero, but provides no algorithm to use for finding it. Now suppose we have a polynomial f of x of degree n. The fundamental theorem of algebra guarantees at least one zero, z sub 1. Then the factor theorem guarantees that f can be factored as f of x equals x minus z sub 1 multiplied by q sub 1 of x, where the quotient q sub 1 of x will be of the degree n minus 1. If this function is non-constant, then the fundamental theorem of algebra applies to it, and we can find another zero. This can be repeated n times. Complex factorization theorem. If f is a polynomial f with real or complex coefficients with degree n greater than or equal to 1, then f has exactly n real or complex zeros counting multiplicities. If z sub 1, z sub 2, and so on, z sub k are the distinct zero of f with multiplicities, m sub 1, m sub 2, and so on, m sub k, respectively, then f of x equals a multiplied by x minus z sub 1 to the m sub 1 power multiplied by x minus z sub 2 to the m sub 2 power, and so on, x minus z sub k to the m sub k power. Example 7. Find all the real and complex zeros of f of x equals 12x to the 5th power minus 20x to the 4th power plus 19x cubed minus 6x squared minus 2x plus 1. Using the rational roots theorem, the possible real rational roots are plus or minus 1 over 1, plus or minus 1 over 2, plus or minus 1 over 3, plus or minus 1 over 4, plus or minus 1 over 6, plus or minus 1 over 12. When factoring a polynomial like we did at the end of the last example, we say that it's factored completely over the complex numbers, meaning it is impossible to factor the polynomial any further using complex numbers. If we wanted to factor the function over the real numbers, we would have stopped at f of x equals 12 multiplied by x minus half to the squared multiplied by x plus 1/3 multiplied by x squared minus x plus 1. Since the zeros of x squared minus x plus 1 are non-real, we call x squared minus x plus 1 an irreducible quadratic, meaning it is impossible to break it down any further using real numbers. It turns out that a polynomial with real number coefficients can be factored into a product of linear factors corresponding to the real zeros of the function and irreducible quadratic factors which give the non-real zeros of the function. Consequently, any non-real zeros will come in conjugate pairs. So if z is a zero of the polynomial, so is conjugation z. Try it now. Find the real and complex zeros of f of x equals x cubed minus 4x squared plus 9x minus 10.